Good day, grade 12 learners. Welcome to today's physical sciences lesson. My name is Dabezinhle Jiwayo. This lesson is brought to you by the Northern Cape Department of Education in collaboration with Pagama Research and Development. In our lesson today, we will be looking at the revision of the section on work, energy, and power, which is part of the mechanics section, which is actually a broad section which carries about 63 marks in our examinations. So we're saying by the end of the lesson, you should be able to attempt typical examination questions on work, energy, and power that is in our paper one document. Right. So looking at the structure of our paper one, remember we are talking about our mechanics section. This is our focus. You can see the mechanics section carries a lot of marks, that is 65 marks. And we were saying our section on work, energy, and power is part of our mechanics section, right? That is being question 5 of our section B. Okay, question 5 of our paper one, and we know that our paper one lasts 3 hours. Right, so grade 12, this section on work, energy, and power has a number of calculations. It implies the use of equations, so it is important that you master the relevant equations to use in different situations. And since it has lots of calculations, it means throughout this lesson, we'll be doing the calculations together. And I should emphasize that together, grade 12s. So ensure that you have a place where you're going to be taking down your notes and doing your calculations. And as such, you should be having your calculator with you. Right, let's start with our pre-knowledge. We're taking our pre-knowledge from our examination guideline, right? So we want to look at what is expected of you in the exam when it comes to work, energy, and power. You do not need surprises, grade 12s. You do not need surprises. So make your examination guideline your best friend, and you know what is expected of you in the various sections. Let's start with the section on work, right? Number one, you are expected to be able to define the work done of an object by a constant force. And I believe we covered this in our previous lessons. If a force F, a constant force F acts on an object, we're saying the work done is going to be defined by F delta X cos theta, where F is our force in newtons and our delta X is the displacement in meters. And theta, remember grade 12s, is the angle between your displacement and the applied force. I hope you remember that. Okay, so, and again, talking about work done, the use of the term work done against a force, the use of this should stop, grade 12s. Okay, this has to be avoided. Work is done by a force on an object. So I know some of us will have the habit of using the term work done against friction. No, the frictional force is a force. It does work on an object. It does negative work on an object. So let's be careful of using such terms. And then in the same section, you should be able to draw the force diagrams and the free body diagrams. And I'm sure you've been practicing that. You should be able to calculate the net work done. The word network there, remember you are considering your diagram, you're analyzing your diagram, you're looking at the forces that are acting on an object. And as such, you should be able to calculate the net work that is done by the forces that are actually acting on an object. Distinguish between positive network and negative network. And you remember positive network energy is added into the system. Negative network energy is taken away into the system. Then we talk of the work energy theorem. You should be able to state these terms. I'm sure that you're taking note of them. There is a definition that we noted from our examination guideline. Definitions are normally 2 marks, and then you may be asked to state the work energy theorem. So these are recall questions. So you should be able to state the work energy theorem. And what does it say? It says that the work done by an object on an object by a net force, take note of that, is equal to the change in object's kinetic energy. Work done by a net force. Are you taking note of that? So we're saying it is equal to the change in an object's kinetic energy. So work net is equal to delta K, which is final kinetic energy minus initial kinetic energy. I hope you're taking note of that. Then you should also be able to apply the work energy theorem now to objects in a horizontal, vertical, and inclined planes, okay, for both frictionless and rough surfaces. So we'll look at typical examination questions to address that. Then we go on to the conservation of energy with non-conservative forces present. So take note again, another definition there. You should be able to define a conservative force as. Are we seeing that, grade 12s? Okay, we give definitions the way they are stipulated by our examination guideline. So if they say define a conservative force, what do we say? We say a conservative force is a force for which the work done in moving an object between 2 points is independent. Take note of that, is independent of the path taken. And we have typical examples, that is the gravitational force, the elastic force in a spring, and the electrostatic forces, which we normally don't deal with anyway when it comes to these conservative forces. And then we are saying you should also be able to define a non-conservative force. You can see this is actually the opposite now of the conservative force. Conservative force, independent. There's the word independent. And look at now, when it comes to our non-conservative force, we're saying the work done in moving an object between 2 points depends on the path. Okay, so typical examples: frictional force, air resistance, tension in a cord, and so on. The light force. Okay, so those are typical examples of our non-conservative forces. Okay, and then you should be able to state these terms, make sure that you know them. As I said, we do not expect surprises in an examinations. When you prepare for an exam, you know what to expect as you are guided by your examination guideline. Right, so we're saying now you should be able now to state the principle of conservation of mechanical energy. What does it state? It states that total mechanical energy, and when you're talking of the mechanical energy, you're talking of the sum of gravitational potential energy and your kinetic energy. So the total mechanical energy in an isolated system remains constant. So it remains unchanged. Okay. So if your system is isolated, you know that the potential energy at a point A will be equal to the potential energy. The mechanical energy at point A will be equal to the mechanical energy at point B. And we're saying a system is isolated when the net external force is actually 0. Okay, so let's remember that. And then you should be able to solve the conservation of energy problems using the work done by your non-conservative forces there is equal to the change in mechanical energy of system, that is the sum of your kinetic energy and the sum of your potential energy. Okay, the changes in the potential and the changes in the kinetic energies there. And then you should be able to use that relationship now to show that in the absence of these non-conservative forces, we're saying our mechanical energy is conserved. Are you taking note of these points, grade 12? Right, then the last part was power. Power. So the first thing, you should be able to define power there as the rate at which work is done. Okay, or at the rate at which energy is expended. Okay, and we're saying power there in symbols is equal to W divided by T, where your W there is the work done and T is your time in seconds. And we're saying you should be able to calculate the power involved when work is done. Right. And then also we have this formula. I hope you remember it from our previous lesson. We were saying our average power is equal to your force multiplied by the average velocity of an object. So looking at a situation whereby an object is moving at a constant speed, and then we're able to apply that formula in rough horizontal surfaces and also in rough inclined planes. And then last but not least, you should be able to calculate the power output of a pump lifting a mass of water. I hope you remember that from our previous lesson on power. Okay, now that being said, let's start our lesson there with a small baseline assessment. Okay, for this baseline, I'm going to give you 2 minutes. Right, welcome back. Welcome back. So we have a multiple choice question there. It says a car moves up a hill at a constant speed. Right? Which one of the following represents the work done by the weight? Work done by the weight of the car as it moves up the hill. Right. So already that word weight, you're already thinking of mass times acceleration to gravity. And if you check there is nothing to do with velocity and so on. So change in kinetic energy, you cancel them out. You're dealing with potential energy. You're concentrating on the what? On the potential energy. So which one is going to represent the work done by the weight of the car? You're going to realize that as the car is moving forward, it's moving upward, we have our weight acting downwards, right? And what is the component of the weight? In which direction is the component of our weight parallel to the plane? It is going to be in the opposite direction, to the direction of displacement of the car. And since it is in the opposite direction to the direction of the displacement of our car, we're expecting this to do negative work. And that serves to direct you that it is going to be equivalent to the change in our potential energy. Okay, and we're saying it is going to be negative. Okay, because it is in the opposite direction to the direction of our displacement. Right, that was our appetizer, grade 12. Let us continue to the typical section B questions. Remember, we said this is typically our question 5. So let us look at this question together and we'll go over it in steps, right? We have a 12 kilogram block, you can see it there, which is initially at rest at point A, at the bottom of a rough inclined plane. Now the block is pulled up the incline by a constant force F acting parallel to the incline. Now the block reaches point B, which is at a vertical height of 4.5 meters above the horizontal. with a speed of 2.25 meters per second, right? So we're getting a lot of information there. Now, define the term non-conservative force. You can see this is a past examination question. Remember the definitions that we cited in our examination guideline. Make sure you internalize all of them, and you know that you'll be guaranteed of these 2 marks. It's either a definition or you're asked to state a principle, and then you get those 2 marks. So remember, we said a non-conservative force is the one for which we're saying the work done by the force on an object depends on the path that is taken. And we gave examples like the frictional force, the tension, the applied force, and so on. Okay, so the work done depends on the path that is actually taken. Are we together? Great jobs. Try to think of it here. I can give you an example. We have the weight, okay, which is a typical example of a conservative force. From our baseline, we discovered that the work done, the net work done by the weight of the object is equal to the change there in the potential energy. Remember, your potential energy is going to be mgh, right? So you can see there is nothing to do with the path. The object is moving here from A to B, that is your delta x. But do we have delta x in our formula there to calculate the net work that is done by the weight? No, we do not have it. We only have the height, which is the final position there. Okay, so in calculating the change in potential energy, you're going to need the initial height and the final height. Those are the 2 variables that will be different. The mass and the acceleration due to gravity will remain the same. So you can see this, the work done there is going to be independent of the path that is taken. But for the frictional force, if you are to calculate the work done by the frictional force, then we say that it's the frictional force multiplied by delta x cos theta. And you can see delta x now is going to be your distance there, your displacement. So indeed, the value of the work done is going to depend on the path that is going to be taken. So remember the definition there for our non-conservative force as well as our conservative forces, right? The next part, calculate the total work done on the block by non-conservative forces. You can see it is in capital, it is in uppercase there for a purpose. The total work done on the block by the non-conservative forces when the block moved from point A to point B. So I'm going to give you 4 minutes for you to work on that part. 4 minutes. Right, welcome back. Welcome back. Let us see how you did this, so you can mark for yourself, do the necessary corrections as we progress. So let's look at the first method. We know that the work done by the non-conservative forces is equal to the change in mechanical energy of our object. And we're saying mechanical energy, the change in mechanical energy is equivalent to the change in kinetic energy plus the change in potential energy. And then how do we find the change in kinetic energy? Half m vf, that is the final velocity minus the initial velocity. And where do you get this? From the question. It started off at rest, that is 0 initial. It ended at b at 2.25 meters per second. All the information is given you in the question. The mass you have from the question. You come to the change in potential energy. Our potential energy, mgh. And we said, what is changing at the heights there, right? Mass is the same, g is the same, 9.8. Final height, you're given there, 4.5. Initial height, it was at ground level, that was 0. Okay, so you can substitute those values. Final velocity, 2.25. Okay, initial velocity, 0. Final height, 4.5. Initial height, 0. And then the job is for your calculator. And we get 559.58 joules. Right, grade 12. Now we have calculated this and you are excited. You got your answer. It's fine. Ensure that you keep this answer somewhere, because you realize that the way our questions are structured, you're going to need this value in the next section. Okay, the questions, they're actually interlinked, right? Let's see how else you could have approached this calculation. Method 2. What can you do there in that case? Right, what do we know? We know that the net work, are you seeing the difference now, grade 12s? We're not talking about the work done by the non-conservative forces, but we're saying the net work that is done is equivalent to the change in kinetic energy of our object, right? And what we know, the change in kinetic energy, half m final velocity squared minus initial velocity squared. All right, and what are we getting there? We're getting a value of 30.38 joules, right? But now the question is, what is our network done comprised of? The network that is done here is going to be comprised of the work done by the weight of the object. Remember, we've got the work done by the weight of the object then. So this is the weight, okay? The weight is going to do some work there on the object. Are we getting it? And we're saying the work done by the weight is going to be the weight delta x cos theta. Okay, and so our work net is comprised of the weight, the work done by the weight, and also the work done by the non-conservative forces. Right. So let's start by calculating the work done by our weight there, which we are saying, right, is going to be mg sine theta. Right. Let me assist you there. Right. Our weight is mg, grade 12, mass times acceleration due to gravity. Okay. Or maybe let's start here to assist you again. Work done by our weight is the weight, which is our FGX there, right? Times your delta X, which is our displacement, multiplied by cos theta. Right, then we're saying, what is this FGX? It is the parallel component of our weight. Remember, this is the parallel component which is acting there in that direction, downwards. This is your FGX. Okay, and then we're saying FGX times delta X cos theta. So what is FGX? This parallel component. If we were to draw a perpendicular line there, we know this angle is theta, grade 12, from our mathematics. And we also know that angle is also what? Theta, right? So the parallel component of our weight, we can draw it this way. Okay, you can see it's opposite theta there. Therefore, we know it's sine theta, right? So this parallel component of our weight is going to be Fg sine theta, which is our mg sine theta there. Okay, delta x cos theta. Are you following? I hope indeed you're actually following. So we are using the parallel component of our weight multiplied by the displacement and then multiplied by the angle that exists now between our parallel component and the displacement. I hope that is making sense, grade 12. So what does that give us? 12 times 9,8, 12 being the mass, okay? 9,8 being our G. Sine theta, we come here, what is sine theta? Opposite. What is opposite? Our opposite divided by our delta x. You can see that. So your sine theta is going to be, you can take this theta, it's just the same, because these two are equal, okay? Let's take this. Opposite is 4,5. Right, let's write it here. Sine theta, opposite divided by our hypotenuse. I hope we remember that from our maths. So opposite is 4,5, opposite our angle. And then What is our hypotenuse? Our hypotenuse is going to be our displacement from A to B, that is our delta x. Do you see that? I hope you can see that. So 4,5 divided by delta x. And then we're saying multiplied by that delta x, don't forget it. And then cos 180. Why are we saying 180? Our displacement is upward. And then we're saying the weight component there is going downwards. And so this gives us an angle of 180 degrees between the weight component and our displacement. I hope you are following it, grade 12. So that and that are going to cancel. And then we solve that, giving us a negative 529 joules. Remember, our idea is to calculate the work done by the non-conservative forces. Right. So where does this take us to now? This is going to take us to that our work net is the sum of the work done by the non-conservative forces, which is the force, applied force, and the frictional force. We know these are the non-conservative forces, right? Plus the work done by the weight, which we just calculated previously. The work net, remember grade 12, work net is equal to change in what? In kinetic energy, right? And we calculated that to be 30,38 joules. The work done by the non-conservative forces, this is what we want. It contributes to the net work that is done on the object. And then the work done by the weight, we found it to be negative 529,2. And then we solve for the work done by the non-conservative forces there, and we get a value of 559,58. So you can see there is two approaches. You choose the one that you are comfortable in. So it's either you are going to say your work done by the non-conservative forces is equal to the change in mechanical energy of your system, which is equivalent to the change in kinetic energy plus the change in potential energy. That is your first method. Method 2, you can say that your work net is equivalent to your change in kinetic energy, okay, which is equivalent to the work done by your weight and also it's work done by the weight plus the work done by the non-conservative forces, right? I hope you are following these calculations, and then you get your 4 marks. Right, let us continue with our question now. It's having now a second twist. So let's follow through this question. The magnitude of the constant frictional force acting on the block while moving from point B to point C is 42 newtons larger than the magnitude. Okay, sorry, we started it in let's start it from the top, the grade 12. Let's start it from the top. The same constant force F now moves the block at a constant velocity across a horizontal surface from B to C. So the force is continuing now. Now, however, it is moving at a horizontal place from B to C. I hope you can see that. Force F acts parallel to the horizontal surface, which is good there. The magnitude of the constant frictional force F acting on the block while moving from point B to point C is 42 newtons larger. Take note of that. The moment you see something in the upper case, take note of it. So the frictional force now is 42 times larger, 42 newtons larger, okay, than the magnitude of the constant frictional force acting on the block when it moves from point A to point B. Quite interesting. Calculate the distance from point A to point B. 5 marks. Okay, so for this part, I'm going to give you 5 minutes. Right. Welcome back. Welcome back. So let us look at this question together. What is it that we know from the question so that we can calculate that distance, delta x? The first thing that we know is that the work done by our non-conservative forces, okay, is actually equal to the work done by our force F, the applied force F. Let's start by looking at that section, the section AP. Let's start at section AP there. Right. So our object is here, grade 12. Right. It is going to be acted on by the force F. Okay. At the same time, we have the frictional force. I'll call it F1 going in the opposite direction. These two forces are our non-conservative forces acting on our object. Are you following? So the work done by the non-conservative forces is going to be equal to the work done by your force F plus the work done by the frictional force. What do we know? We know that your F, okay, the work done by the force F, okay, is equal to F delta X cos theta. Your F is in the direction of displacement. So the angle is going to be 0. Remember, delta X is what we want to calculate, okay? So we have our value of our force there, which is F. Then the work done by the frictional force is going to be F1. We say our frictional force is F1. Delta X cos 180. Why 180 grade 12? Now I believe you know that the frictional force is acting in the opposite direction to the direction of the displacements. Hence, the angle between your displacement and the frictional force is going to be 180 degrees. Okay, cos 0, we know that is a 1. Okay, cos 180, we know that is a negative 1. Okay, the work done by the non-conservative forces, remember I said keep that value. We calculated it to be 559,58. You still remember? Let us simplify this formula. Okay, remember we said F delta X cos 0, right? I just want to simplify this with you. Some of us might be lost now. F delta F1 delta X cos 180 degrees. Take note, cos 0 is a 1. Then we say 1 multiplied by F delta X. What do you remain with? You remain with F delta X grade 12. And then we say plus, you have your F1 delta X. And then cos 180 there is going to be a negative 1. Okay, so this translates to F delta X minus F1 delta X. So what do? We factorize. Common factor there is delta X, right? Then what do you remain with? You're going to remain with F minus F1. Okay, so we are going to take this now as our equation 1. Remember, this is on the right-hand side, and we're saying it is equivalent to the work done by the non-conservative forces. I hope it is making sense. This is our equation 1. We're deriving it from point 1, from point A to point B, right? Let us proceed there. Let's just erase this and explain a few things again, grade 12. Then let's go to point B and C. Let's analyze that thing there between B and C. What do we know? Remember, we said the frictional force that is acting between A and B, we will call it F1. So we're going to call the frictional force that is acting between B and C, we will call it F2. Right. What are we told then? Take note here, this object is moving at constant speed between B and C. Right? So what is the net force that is acting on our object there? The net force is going to be F minus F2, which is our frictional force between B and C. And we know that in accordance to our Newton's second law, this is going to be equal to the mass multiplied by our acceleration, ma. But since our object is moving at constant velocity, it means your acceleration is going to be 0, so which gives us your F minus F2 is going to be equal to 0, right? But then what do we know about F2? If we come here, we're told the magnitude of the constant frictional force acting on the block while moving from point B to point C is 50 newtons larger. So what does it mean? It means your F2 is actually equal to F1 plus 42. Is that making sense? Because F2 is 42 newtons larger. So F1 plus 42 is going to give you F2. So let's substitute there. So we're saying F minus F1 plus 42 will be equal to what? Will be equal to 0, right? Let's remove the brackets there. F minus F1 plus minus is going to be a negative 42, giving us 0. We're already seeing something familiar here. You see, we have a F minus F1 there. Okay, so what is F minus F1 equal to? F minus F1 is equal to 42. We're taking the negative 42 to the other side. So this is our equation 2. So now it means where we have F minus F1, we can substitute what? 42, so that we can get our delta x. I hope that is making sense. So let's substitute there. In place of F minus F1, we're putting our 42 there. So we can divide both sides by 42 and we get a value of delta x of 13.32 meters. So that is going to be 13.32 meters. Right. Quite an interesting calculation there, grade 12. I hope you were able to do that calculation. Right. Let us go to question 2. Question 2. Now, another typical examination question. Now, for this part, I'm going to give you another 5 minutes. Right, welcome back. Right, let's start with the first part. A roller coaster of mass 200 kilograms with the engine switched off. So, okay, travels along a track ABC, which has a rough surface, as shown in the diagram below. At point A, which is 10 meters above the ground, the speed of the car is 4 meters per second, right? Then at point B, which is at a height h above the ground, the speed of the car is 2 meters per second, right? During the motion from point A to point B, 3.40 times 10 to the power 3 joules of energy is used to overcome friction. Ignore rotational effects due to the wheels of the car, right? Now define the term non-conservative force. Do you see we're meeting this question as is, and these are two separate examination questions from two separate years. So know your definitions, grade 12. And we said non-conservative force is one for which the work that is done by the force on an object depends on the path that is actually taken. Remember that. And then you get your 2 marks. And then we say calculate the change in kinetic energy of the car after it has traveled from point A to point B. So you're looking at change in kinetic energy, delta EK. What you need to remember now is the formula, grade 12. Change in kinetic energy. The moment you're dealing with kinetic energy, you know it's half mv squared. So you need the change. You are saying the final velocity f squared there minus the initial velocity squared. So these are the things that you need to search for from the question to get your change in what? In kinetic energy. So you list your data here and you say, okay, what is my mass? you come to the question, my mass there is 200 kilograms. All the information you need is there in the question. Final velocity, my VF, okay, VF, just my final velocity. You come to the question, okay, remember you're told between A and what? And B. So what is the velocity at B? That is your final velocity. You are told now at point B, which is a height h above, the speed is 2 meters per second. So that is your final velocity, 2 meters per second. Then what is your initial velocity, grade 12s? The velocity at point A, we're told at point A, it is what? It is 4 meters per second, grade 12s. Yes, I hope you got those. So we have the mass, we have the velocities. We can substitute now into our formula. So change in kinetic energy is equal to final kinetic energy minus initial kinetic energy. So we can substitute there into our equation: mass, final velocity, initial velocity, and we're getting a value there of a negative 1,200 joules. This is our change in kinetic energy. Right. I hope you got that correct. We go to the next part. Use energy principles. Use energy principles to calculate the height h. We need to get h there. So what can we do? We can say that we know that the work done by the non-conservative forces is equal to the change in mechanical energy of our system. And then what are we saying then? The work done by the non-conservative forces is equal to the change in kinetic energy plus the change in potential energy. Do you see the trick there? In the change in potential energy, we're interested in the height, HF there, the final height. We're putting it on mgh, right? And then we have the initial height at A there. Okay, so you need to identify all these values, grade 12s. The work done by the non-conservative forces, you are given there during the motion, 3,4 times 10 to the power 3 joules is used to overcome frictional force, which is your non-conservative force. So this energy is the work done by the non-conservative forces. And you're talking about friction, so we know that negative work is done. So it's a negative 3,4 times 10 to the power 3 joules. Take note of all the detail, grade 12s. And then the change in kinetic energy, we did that in the first part, which is a negative 1,200. Okay, then M, then we have your G there. Final height is the one which you want to calculate. Okay, and then the initial height is 10 at A, you're given, right? So this is your initial height, which you can call HI. This is your HF, the one which you want to get. And the rest there now, we're solving our equation, right? So we can solve our equation there and we get a height of 8,88 meters. I hope you are finding these questions quite interesting, grade 12s. All right. And then the next part now, on reaching point B, the car's engine now is switched on. Quite interesting. Now, in order to move up the incline at C, which is 22 meters above the ground. While moving from point B to C, the car travels for 15 seconds at constant speed of 2 meters per second, while an average frictional force of 50 newtons acts on it. Calculate the power delivered by the engine to move the car from point B to point C. And now, just as a reminder, remember, power is work done divided by time. And in this case, don't forget, you need the work done by the engine, right? So that you can calculate your power. The time is given there, 15 seconds, right? And that being said, I'm going to give you 5 minutes to do this calculation. right. Welcome back. Welcome back. Grade 12s. Can you look at the solution of your neighbor? Check. Check. Are you getting the same values, guys? Are you getting the same values? Let's see how you did it, and let's see if you actually got it right. So remember, the work done by our non-conservative forces. Okay, the work done by our non-conservative forces is equivalent to the change in mechanical energy of our system, right? But which are the non-conservative forces that we are having there? We are having the force of the engine. Let me call it FA. The force of the engine, right? One non-conservative force. And then what else? The frictional force. These are the two non-conservative forces. So the work done there by the non-conservative forces is equal to work done by the engine, the one that we need in our power formula there. Remember grade 12. And T we already have, right? And then we're saying the work done by the frictional force. Are you following there? And then change in kinetic energy, we now know the formula. Change in potential energy, we also now know the formula. But now what is important is when you are to substitute these values, remember, if you are to substitute these values, you should know what is my formula for calculating the work done by the friction. F delta x cos theta. Right. So you need to be able to do that. And we're saying F delta x cos theta. The frictional force you're told is 15. Okay. What is our delta x? Our delta x there is given 15. How do we know our delta x is 15? Grade 12. How do we know our delta x is going to be 15 multiplied by 2? Take note there. This is our delta x. Okay. You get the information from the question. Look at the question there. The car travels at 15 seconds, for 15 seconds, at a constant speed of 2 meters per second. So you have time, right? So your delta x is going to be what? Is speed multiplied by time. The speed is 2 meters per second. The time is 15 seconds. So you have your time, you have your speed. So these, they give you delta x. I hope you're following. Cos 180, that is the angle between our frictional force and the displacement. Okay, so this is the work done by the friction there. Okay, and then we come to our change in kinetic energy. Interesting then. Change in kinetic energy is 0 because we're told this is moving at a constant speed of 2 meters per second. The velocity is not changing. So it means we are having no change there in kinetic energy. So it's going to be 0. Our mass is 200, our G is 9.8, and then the final height, our final height is 22, our initial height. We're moving from HF. Remember we calculated this one. Our HF was 8.88. You remember that in the previous question? Yes. So that was 8.88. Okay, so now you can substitute there and we get the work done by the engine to be 227,215.20 joules. Now we have found the work done by the engine, so now we can substitute in our power formula. Power, work done by engine divided by time. The work done by engine, we found that, and our time was 15. Therefore, the power of our engine is going to be 1,814.35 watts. Right. Quite an interesting calculation there, grade 12. Right. That being said, this brings us to the end of our lesson for today. As usual, here is some homework there. You can take a picture of this question so that you are able to work it out. So you can just take a snip of the first part, okay? And then this is the second part of our question now, right? So you can also take this part again, grade 12, so that you you practice. Right. Now, that being said, remember the key things that we spoke of in our lesson. We spoke of the mechanical energy of the system is conserved only when conservative forces are present. Okay, so that is the initial mechanical energy is equal to the final mechanical energy. Mechanical energy being comprised of your gravitational potential energy and the kinetic energy of an object. And we're saying when there is non-conservative forces, we know that the mechanical energy of our system will not be what? Will not be conserved. And also remember that the work done by the non-conservative forces is equal to the change in mechanical energy of our system. And then the net work that is done on an object is equal to the change in kinetic energy of our system. Right. I hope you really enjoyed these calculations that we had in our section on work, energy, and power. I know it might be a challenging section, but you know what? Practice makes perfect. Practice, practice, and practice. Okay, so look for many examination questions and you go over them. Remember the pointers that were given by our examination guidelines, the definitions that you need to know, the principles that you need to know, the formulas that you need to know, how to apply them, the calculations that you also need to know. They are all there in your examination guideline. So in our next lesson, we shall be looking at the section on waves, sound, and light in particular, that is the Doppler effect. And we're looking at how the movement actually affects the frequency that is actually heard by an observer from a source. So you can see that we have a source there, which is an ambulance, which is actually liberating some sound of a particular frequency. But because of the fact that it is moving, the observer is going to hear a certain pitch. The pitch is going to be higher because of a decrease in the wavelength of the emitted waves. The decrease in the wavelength implying a higher frequency. And as the object moves away from an observer, you can see now that the wavelength is going to increase. So the wavelength, meaning that you're going to have a lower frequency, hence a lower pitch. Okay, so you can see the differences that we have there on the two observers. So we have those changes that happen when the source is moving towards the object or when the source is moving away from the object. So I hope you are going to read ahead on this section. Right. That being said, our work is done for today, and I hope actually God blesses you. Till we meet again, enjoy your day.